Still in focus? Okay. Okay, so welcome everybody to lecture number 4. And I hope you had a good weekend and you're not getting too stressed out with ICML deadlines and all that. Okay, so today we are going to start looking at an application of optimization, namely an algorithm for performing MaxCUT. The nice thing is that the basic idea that underlies this algorithm will come in useful also on Wednesday when we look at binary hashing, so something called a SimHash. It's quite an important idea because this one simple idea actually has led to 2 best paper prizes, so it's actually quite a substantial paper and quite a substantial idea to think about. And so you might feel intimidated, you know, 2 very well-known people got a best paper prize. You know, what is this very complicated idea about? Well, actually, it's very simple. So in a nutshell, here's what happens. If I have 2 vectors, let's call them x and x prime, and let's say they are of unit length, and there's some angle phi in between, and I'm going to refer to this angle occasionally as arc cos of x dot x prime whenever the length of those vectors is 1. And if I take a random hyperplane, so this holds obviously in a plane but also otherwise, so basically I take a random w and I look at the probability that this random hyperplane splits x and x prime, then this probability is given by phi over pi. So basically I'm interested in the following probability, that the sine of x dot w times the sine of x prime dot w, this thing here, is less than 0. This is given by phi over pi. This simple idea will let us do a lot of cool things both today and also on Wednesday. And the point is basically that it will let us approximate inner products between x and x prime by suitably drawing binary vectors. And it will also let us estimate inner products quickly by just storing binary signatures. So the latter is something that we're going to use on Wednesday. The former is something that we're going to use today. And it's related to something called Grothendieck's identity. And this is around 1950. Interestingly enough, in the paper by Goemans-Williamson that we're going to go through today, largely there's actually no such reference to that. This was only realized later on. So the primary reference for today is a paper by from 1995. Okay, good. So before we get into this paper, let me introduce a couple of tools. And those tools are going to be useful both for the context of this class today, but also later on. The first thing that we need is what's called a semidefinite program. Who has seen semidefinite programs before? Okay, good. So who knows what the second order cone program is? Okay, fewer people. Good. So then there's probably no harm in showing this. So first of all, well, what are positive semidefinite matrices? let's say I have some matrix K, and I write it as so. And this is equivalent to saying that for all vectors x, we have that x transposed kx is greater or equal than 0, and furthermore that k equals k transposed. So these are just positive semi-definite matrices. In other words, all the eigenvalues are greater or equal than 0. So the first useful thing to note about those matrices is that they form a convex cone. So in other words, if I have two matrices K and K prime in this set, in this cone, then it follows that lambda K plus lambda prime K prime is also in this cone for all lambda prime greater or equal than 0. So this is a slightly stronger condition than just convexity, which would have the requirement that lambda plus lambda prime equals 1. Here we just require that they are both non-negative. Okay. Do you have a question? Okay. So to prove this is actually very trivial. You just apply x to the sum, and you can see that obviously, since this all decomposes, x transpose kx and x transpose k prime x are both greater or equal than 0, so this condition holds. So this is easy. Now, the primal form of a semi-definite program is often written as follows. I want to minimize the trace of some matrix X subject to the conditions, actually C times X, subject to the conditions that trace of AIX less equal than BI. So far, this would be a linear program, right? Because I haven't imposed any constraint on X yet. I've just written it in a funky way. Even the fact that X needs to be symmetric, I still could, turn any linear program into one of those by just, copying the entries. I might have some, leftover constraints, but nothing has changed yet. The key difference is that I also require that X be positive semi-definite. So I might occasionally have equality constraints. Sometimes the equality constraints would be horribly inefficiently written through matrices A. So in some cases, it's easier, for instance, just to say xij equals 5. But in the functional form, they're exactly that. This is often called the primal version of the problem. What I'm going to write out now isn't exactly the dual, but something that is very similar to the dual that you will get out of this. And it's written as follows. And here we need to optimize over x. Here also x, but here x is just a vector. C transpose x subject to, well, we usually have our ax less equal than b. And furthermore, the sum over some matrices mi xi has to be greater or equal than some m naught. Okay. So again, in some cases, this may be hideously inefficient to write it like so. But for instance, in learning the kernel problems, you often have that kind of formulation. You might have some candidate kernels. You want to make sure that the linear combination of whatever you're taking is still a kernel. So m naught might be actually 0. Or maybe you want to make sure that none of the eigenvalues is too small. So you would have m naught being, lambda times the identity for some very small lambda. So all of those forms are possible. So basically, the key difference is that here we actually have a linear combination over a bunch of matrices, and that needs to be positive semidefinite, whereas here we just optimize over the matrix directly. This is sometimes easier to deal with because you may have quite often fewer variables, but then you might have a harder time ensuring that this constraint is satisfied. Okay. So this is what's often referred to as a dual of that problem, but it's not really strictly speaking the dual thereof. In the recitation, we're actually going to see forms of linear programs, quadratic programs, semi-definite programs, possibly second-order cone programs, and see what their duals look like, just such that we can easily go through those problems. By the way, if there are any questions, ask, right? Okay, because this way it helps you find figure out what's interesting. It also helps me to find out how fast I should go. Okay. So, quick question. Is this still a convex problem if I impose a rank constraint? Let's say if I require that X has rank 1. Who votes for yes? Okay, nobody. Who votes for no? Okay. Given that you all had your hands up, why is it not a convex problem anymore?
The set of all rank 1 matrices is not a convex set.
Okay, sure. So, proof. Why is it not a convex set?
You take any two rank 1 matrices, you take the convex
Exactly.
in a rank 2.
Exactly. We could take, for instance, this matrix. This is a rank 1 matrix. And I take that matrix. And so if I add a weighted combination of those two together, I'll get a rank 2 matrix. And this is why a rank 1 constraint will break it. Okay. So those problems look fairly innocuous. The bad news is that in order to solve them, you actually have to usually expend a very substantial amount of computation. So it's not uncommon if you have to spend order d to the 6, where d is the dimensionality of x, in terms of computation. So don't be fooled by those problems looking nice and being tractable and all that, and people will tell you, yeah, it's just an SDP. Yes. The reason why this is d to the 6 has a lot to do with the fact that if you need to invert a matrix, it's cubic. But here we actually have a quadratic number of entries, so we have order d squared entries. Now if we have to invert the equivalent of a d squared by d squared system of equations, well, we'd pay order d to the 6. That's the reason of why you get this. In some special cases, you can get cheaper, and then there are approximate solvers which will let you do interesting things. Bottom line is, you almost certainly do not want to code this up yourself. There's a number of open source SDP solvers around, and if your problem formulation doesn't fit that one directly, there are actually conversion tools which will formulate or reformulate your problem into either this or that form. There's, for instance, something called YALMIP. Yet another linear matrix inequality parser. Okay, so that already tells you that this thing is actually highly fault prone, and that you can easily mess this up. So basically use software. Okay, good. Before I continue, let me also briefly mention second order cone programs. Because, this is clearly a cone, but you can make cones also in another way, and they are often referred to as SOCPs. And basically, what you have is constraints of the form AX plus B to norm less equal than C transpose X plus D. And if you squint at this hard, you can see that first of all, this is a convex constraint, and secondly, this is non-empty for certain choices of A, B, C, and D. So you can easily find out about stuff like this. Let's say you have a cone along one axis. Then you can see that the radius here, right, this radius is going to be some function r equals, C times x1. And so all you now need to require is that, let's say, x2 squared plus x3 squared, square root thereof, is less equal than C times x1. Okay? And this gives us exactly this cone where it's a circle along the second and third coordinate. So these programs turn out to be slightly easier to solve, even though if you look at them, they don't really look like that. Again, if you can avoid it, do not implement it yourself. Okay. I'll leave it at that. We might come back to those later during the class, but probably not this week. Okay.
And the objective function is still linear in X?
Yes, you would still have a linear objective function in X. You may get cases where you have a quadratic objective function in X, and then you can reshuffle some terms around. More generally, in most machine learning cases, you just have a convex objective, and then second-order cone constraints. And then you probably have to do some work on your own. Sometimes by moving to the dual, a lot of the terms get collected in the same place. You can rewrite them in some cases by, for instance, adding slack variables. And this way you can make a nonlinear objective linear and just put things into the constraints. So you can do stuff like this. So just to mention this, suppose I have something like minimize some function f of x subject to c of x less equal than d. Right? So we have a convex constraint and some objective. Let's say I want to linearize this. I can make it equivalent to minimize over some variable t. So this is now, I'm adding a slack variable here, minimizing over x and t, subject to c of x less equal than d, and furthermore f of x less equal than t. So by doing this, I've turned this general convex optimization problem with convex constraints into one which has a linear objective and convex constraints. So this is, for instance, a useful trick if I want to move things from the objective into the constraint set. Mind you, this is something that, let's just say, has led people in support vector machines to writing more than one paper about the same algorithm because they didn't realize this. And you could get away with it because the referees didn't realize it either. Okay, those times are fortunately past. Okay, good. So this is what I want to say about optimization. Now let's, because the entire class is advanced optimization and randomized algorithms, let's at least briefly talk about randomized algorithms. So the property that I'm going to exploit today is that I'm going to design an algorithm where the expected value of the output of the algorithm is going to be well behaved. And then this is going to help us obtain a solution such that at least if I try often enough, I'm going to get a solution that's good enough, that's going to be good enough relative to the expected value. We will later on get other algorithms where you average over terms, and the average is going to be good enough. Or where we will go and take the median, and then we'll average the medians, or we'll take the median of the averages, or other things of that form. And this will ensure that we will actually have statistically well-behaved quantities with error bounds and so on. So what I'm going to do today is just very briefly start off with a rather useful bound. It's called the Markov inequality, and it goes as follows. Suppose I have some random variable x, and it's drawn from, p of x, and x is greater or equal than 0. Okay, good. So I can look at the expectation, mu. This is the expected value of x, so this is the integral from 0 to infinity of x dp of x, right? So this is obviously greater or equal than the integral from some constant c up to infinity of x dp of x, right? This holds for any c greater or equal than 0, right? Which is, again, greater or equal than this constant times the integral going from the constant to infinity of dp of x. So what we've just proven is that the probability of x being greater or equal than some constant c is less equal than mu over c. Okay. So this is obviously useless whenever c is less than mu, because then we just show that the probability is less than, let's say, 1.5, though. But whenever we have some random variable that characterizes something that bad happening, we know that this random variable is non-negative. Then we can, for instance, ask, what are the chances that things are at most twice as bad as on average? And those are actually kind of useful quantities to have in the context of the Kant-Min sketch. We'll actually get to this, and we'll see how this can let us get good, estimates. Okay. In our context right now, this is not immediately useful. What I'm actually going to do is what I want to do is I want to get something where later on we get a randomized algorithm with a certain mean, and I want to make sure that it's not much worse than the mean. Okay? So actually that's also very easily obtained, right? Let's say here's the mean mu. So what I'm going to do is I want to get something that's not too much worse than the mean. Let's say mu minus epsilon, right? And so for that, I need an upper bound b. I need to know that, this is going to be, my random variable is going to be less equal than this upper bound. And so what I can do is I can just define a new random variable. Let's define y equals b minus x. I know that this random variable here is greater or equal than 0, since x was less equal than b. Okay. And then all I have to do is just look at the probability. Okay. Furthermore, if mu was the expected value for x, then I know that the expected value for y is simply b minus mu. And then all I do is I get that the probability that, x is at least mu minus epsilon is going to be greater or equal than 1 minus, and here we have b minus mu divided by b minus mu minus epsilon. And then if you work this out, you'll get exactly that this is just epsilon over b minus mu minus epsilon, which is, of course, greater than epsilon over b minus mu. Okay, done. So why would I need this? Because if I later on design an algorithm that has a random variable with a given guarantee on its expectation, and I know that this random variable is bounded from above, then picking any epsilon where this epsilon is, is non-zero, I know that if I just try often enough, I'm going to get a random value that is at least mu minus epsilon good. Well, which kind of sounds obvious, but okay, it's kind of useful to show this. By the way, does somebody have a good idea of a counterexample why I need this upper bound b? What could happen otherwise? What happens if b is large? If b is large, then, well, this quantity gets really tiny, right? Does any suggestions of when this could happen in reality? Well, a lottery has that property, right? One guy wins, everybody else doesn't win, right? So maybe the return on this lottery ticket is maybe, 0.1 on, $0.1 on $1 investment. Now, however, nobody gets anything, and well, the winner gets, some crazy high number, whatever it is. And in this case, I would have to draw many, many, many times until I finally actually win the lottery, right? So this is an example where b would be ridiculously large, and I would have to keep on trying a long number of times before I actually see something. And that's exactly what we want to avoid. Okay. Good. Any questions so far? Okay. So now let's return to the Grothendieck inequality. And let's actually look at what happens for this. So I'm going to define a random variable y. And this is going to be defined as the sine of w dot x. Okay. So if I have y prime, these correspond to x and x primes. If I have xi, xj, I'll have yi, yj. So now what we have is that the expected value of y prime, this implicitly depends on x, is, of course, nothing else than, well, here we have basically what are the chances that, this is 1. So this would be 1 minus phi over pi minus then phi over pi. That's basically the probability that the two signs match. This is the probability that the signs do not match, in which case I get a negative contribution. So it's basically just 1 minus 2 over pi phi. So I can also write this as arc sin of x prime, and I have a 2 over pi here. Another quantity that we'll often care about is the following. The expected value of 1 minus y prime over 2. So what this does is clearly it's 0 whenever y and y prime disagree. Sorry, whenever they agree, it's 0. And whenever they disagree, it's 1. Because whenever they disagree, remember, they are plus minus 1 valued variables. So whenever they disagree, this is minus 1, so I get 1 minus minus 1 is 2 over 2 is 1. Otherwise, it's 0. So this is simply phi over pi actually, yeah, that's it. And so I can write this as arc cos of x prime over pi. Okay. So what I'm going to do with those variables now is I'm going to relate them to the inner product. And what we'll see is that, quite surprisingly, the value of the inner product and the expectation of y prime, and correspondingly 1 minus y prime and this, they're going to be fairly close. The reason why this is interesting is because I can therefore then replace problems where I need binary rank 1 objects by full rank objects with a suitable factorization, which is exactly what Goemans-Williamson is going to do afterwards. So the two pictures to remember are, first of all, let's just plot 2 over pi arc sin of x in x prime versus x in x prime. I'm just going to use the value t, and here's t, and here's 1, 1, 1, and 1. And we know that it has to cross 0. We also know that for the value 1, it's going to be 1, because this is exactly going to emit pi over 2 or minus pi over 2. So these match. And what actually happens is you get this curve. Okay. And furthermore, there's the slope here, which comes in at 0.638. Okay. It's kind of useful. More interesting, though, is the second function here. And this one behaves as follows. Basically, all I'm doing is I'm just shifting the coordinate system. I'm just shifting it from here to down there. Same function again. And there's a reason why I'm drawing this picture, because it's going to come back so many times. 1, 1. And here I'm going to write arc cos t over pi. And here I'm going to write t. Actually, here I'm going to write 1 minus t. Over 2. So I'm basically I'm relating this and that quantity, basically. That's what I'm going to do. And this function has that property, same function, right? Because this is just trigonometric rewriting. And this one has a slope of 0.878 and something. I'm going to refer to this quantity as alpha. Okay. Now, this sounds like, giving those functions a little bit more attention to detail than I should. But this is actually going to be the approximation that I'm going to use over and over and over again throughout this lecture today. Okay. So basically, what we're going to do is we're going to turn problems that require this expression here into problems that will use an inner product between vectors of unit lengths. And then afterwards, we're going to use a randomized algorithm to discretize that again to values of 1 and minus 1. And then we're going to show that by first relaxing, which of course gives us a better objective function value because we relax some constraints. And then by approximating, we're going to get a solution that's almost as good as the optimal and typically NP-hard solution. So this is essentially our argument. So in other words, if this is the solution quality, here's the problem P that we want to solve. Then P SDP is going to be larger than this, because we're going to relax some constraints. And then we're going to show that, well, in this case, 0.878 P SDP is going to give us a feasible set of variables for this problem. And so therefore, it's going to also be a 0.878 lower bound on P, because I don't know where P sits relative to SDP. Okay, yeah, here's the origin. Okay. This is the idea of pretty much all the arguments that will follow today. Okay. Now, after such a long lead up of about 45 minutes, I'll finally tell you which problem we're going to solve today. It's called the MaxCUT problem. And it essentially has the following form. I have some graph. And this graph has some set of vertices, some set of edges. And those edges have the property that they have a weight Aij I going to j attached to it. And I'm interested in finding the maximum cut between I and j. So I'm basically interested in finding the cut that is the most valuable, the most expensive, the most interesting in whichever other version. Okay. So basically, I'm interested in find some variables yi in plus minus 1 such that the sum over I and j of 1 minus yi yj over 2 aij is maximized. Okay. So that guy again, right? It's the reason why we have this curve here. So you can clearly see if I is not equal to j, this is going to be negative, so this is going to count as 1. Whenever I equals j, it doesn't count. Okay. So this is the goal. There's a lot of problems that you can rewrite in this form, but the point here is this is a discrete optimization problem. It's not easy to find. So what we're now going to do is we're going to see a first example of where relaxing the problem, basically loosening up the constraints, will obviously give us an upper bound, and then we apply a cleanup procedure to make sure that this relaxed problem can be turned into something useful again. So I'm going to rewrite this problem in a, well, maybe not so beautiful way, but it's kind of necessary. So I can write this as maximize over all the y's with the following condition: sum over I and j, 1 minus yi yj over 2 aij, subject to the constraint that yi rm plus minus 1. Okay, nothing has happened yet. So now I'm going to replace this by another matrix K. Ij. And I'm going to require now that this matrix satisfy the following condition. And it's not a complete coincidence that I'm calling a K like kernel. Kii equals 1. And furthermore, K being positive semidefinite. And furthermore, that the rank of K equals 1. So you can immediately see that those conditions imply that Kij has to be written as yi yj. Because if the rank of a matrix is 1 and if it's positive symmetric, so I know that this has to be written as V transpose. In other words, Kij is Vi Vj. Knowing that Kii equals 1 means Vi squared equals 1, so Vi can only be plus or minus 1. So therefore, this is entirely equivalent. So this is an equivalent problem to the MaxCUT problem. Now comes the key step. Can somebody guess what the key step is going to be? I'm going to cross this out. So I'm basically going to drop the constraint that the rank of this matrix is 1. Okay. I'm going to keep this condition. I'm going to keep the condition that it's positive semidefinite, but that's about it. Okay. So if you look at the problem then, you'll see immediately that this is a semidefinite program, right? Because we have the trace between two matrices, the trace between K and A that we want to maximize. We could minimize the trace between K and A. Everything else just goes away anyway. Subject to some equality constraints, Ki equals 1. Okay, we could turn this into an equality constraint. And a positive semidefiniteness constraint. That's it. Okay. So now we're almost done. Because now we have actually those matrices, we'll get a matrix K. The question now is, obviously we've gone from here to PSDP.
if you remove the rank k equal to 1 constraint, then it will not remain equivalent to the original.
No. So what we've done is we've gone from here to there. Right? This is by dropping rank k equals 1. This is how we go from here to there. So what we now need to do is we need to extract from this SDP solution, which is going to give us an upper bound, something that is feasible and where we don't lose too much in the process of getting feasible. Okay. So how do we do this? Well, actually it's very easy. It's surprisingly easy. We perform a Cholesky factorization. So I'm going to write k equals v transposed. Let me just write it out. Okay. Who's heard of a Cholesky factorization before? Okay. So basically what it does is, and you could use any other factorization of this matrix into some matrix and its transpose. But Choleskys are kind of easy, and your laptop can do this. It basically turns a square matrix, positive semidefinite matrix, into this. It's basically a triangle times a triangle transposed. You use this also for solving linear systems of equations. So in general, whenever you deal with k and you want to solve a linear system, do this. Never write inf of k. This is numerically horribly unstable, unless you have a really good reason for ever needing k many, many times and other things. Otherwise, always work with the factors. Because solving for a triangular matrix is order d squared, whereas inverting this is order d cubed. Mind you, we don't get anything for free because obtaining this factorization is already cubic. But it's numerically much more stable. The other nice thing is that it's a rank-revealing decomposition. In other words, if the matrix doesn't have full rank, then this thing will simply stop somewhere, right? And this will be all 0. Okay. So now we have this. A really useful property of this is that these row vectors in here, or column vectors in there, are all of unit length. They have to be of unit length because we kept this constraint kai equals 1. Because we know that kij is just vi vj, where vi and vj are the corresponding row vectors or column vectors, depending on how you look at it. Okay, good. So now what I'm going to do is something very simple. I'm going to draw w from a normal distribution in d dimensions. And I'm going to use y equals sine of v times w. This is now, again, a binary vector. And so now the question is, how good is this binary vector going to be? So this is the step going from here to there. Y equals sine VW. Okay. And so this is exactly why we cared about this expectation. Right. So this is exactly the arc cos. And we know that the arc cos is going to be at least alpha times this. So we know that in expectation over W, the sum over I and j, Aij, 1 minus yi yj over 2 which is obviously nothing else than sum over I and j aij are cos, and it's 1 over pi, and we had the kij is going to be greater or equal than alpha times sum over I and j, and here we have 1 minus kij over 2 aij. And so we're done. Because we know that this, without the alpha, is an upper bound. So we've basically sandwiched our problem that we want to solve, and that's hard. By an SDP relaxation, that's easier. And then from that, drawn a random variable. That's also easy. And then, by just applying this often enough, we'll find at least one solution that's as good as its expectation. That's the idea. So this is one of the nicer, simpler examples of where randomized algorithms and optimization meet. So I basically have a non-trivial combinatorial optimization problem. I then relax it to get a convex, somewhat less non-trivial optimization problem. I then use randomization to get, again, a combinatorial guesstimate, which I then prove is not too bad relative to what I should have done. Okay. So there's a couple of things that we can do directly with that. First modification that we can make, and I can actually ask you guys how you would do this, because these ideas are simple now. Okay. Suppose I want to do a MaxCUT, and I want to make sure that pairs of variables are in the same set. How would you encode this? Basically, that there are certain edges that you're not supposed to cut. Exactly. What does the constraint look like? Exactly. Perfect. So kij equals 1. From that, it follows that yi equals yj. So that you could probably eliminate the variable, which would make the problem slightly faster. However, in this place, you cannot eliminate the variable easily. Kij equals minus 1, from which it follows that yi is simply not equal to yj. You don't know what the values are, but you know that they're not equal. Okay. So this is easy to do in this set. Now, the couple of interesting modifications. So the first thing is to observe what happens whenever the problem is actually really easy. In other words, I can get a value that's very close to the maximum. This means that we are effectively here in this regime, right? And so you can see as this approaches 1, of course also, because I mean this is basically what I get through expectation, this is what I get through the relaxation, those two quantities converge to each other. So what that actually means is that if I have a solution that is very large relative to what it could be, then I know that the approximation quality actually is even better than it would have been in the worst case. You can turn this entire thing into a proof, and details are in the Goemans-Williamson paper. I'm not going to go through this in a lot of detail, but basically what you need to do is you need to look at what the value of the SDP solution is relative to the maximum value that you could obtain by putting everything, by cutting everything. right? And then you basically argue your way up here. Okay. What's a little bit more interesting is to consider the situation when I have negative weights. Because this can actually happen. Because so far, in our entire analysis, we require that the aij's are non-negative. Can somebody tell me where we use this? Because we clearly used it somewhere, right? Fun? So basically, we used it because we had the product between two factors. Both factors are non-negative, and we had an inequality for one. If the other factor is negative, the inequality goes the wrong way around, and we're screwed. So that's basically where we used it. So we used it in combining this with aij. So what you do in that case is you actually tease apart the positive piece and the negative piece. And then you show an inequality for that, and you work your way backwards. Okay. So let me walk you through this in a few details. So basically, what I'm going to do is I'm going to look at the sum over I and j, aij. By the way, without loss of generality, I'm assuming that aii equals 0. Otherwise, I just need to explicitly eliminate this from some sums. Well, not here, but in some other cases, I would have to worry about it. So aii equals 0. So it's just to make my life a bit easier. So I'm going to look at this. Okay, we have 1 minus yi yj over 2, as we had before. And I'm going to also subtract from that minus a minus, and that's basically the sum for all the I and j's, where I have that aij with a property aij is less than 0. Let's call this thing here a minus. A minus is negative. Subtracting something negative is going to add to it. And what I want to show, it's a lemma, that this is greater or equal than alpha times, here we have the same inequality again, ij, aij, 1 minus kij over 2 minus a minus. Because obviously if I have this, I can move the a minus to the right-hand side. So this is equivalent to this being greater or equal than alpha times sum over ij, aij, 1 minus kij over 2 minus, and then here we have 1 minus alpha a minus. Sorry, plus. Yep. So in other words, if I have negative terms, I have to pay for them and my inequality gets worse, but it only gets slightly worse. So I basically have to sum over all the negative entries, and I pay for them a cost of 0.122, right? So rather than paying full price, I pay for them only that much. So to prove this, I don't know whether you want me to go through it in a lot of detail. What you do is you basically decompose the sum here into the positive terms and the negative terms. For the negative terms, you match things up. Okay, let me do this. No, this is not good because I actually need this. Okay, let's see. Okay. Or I can actually write it here. Yeah. This is probably less ridiculous. Okay, so we have expectation of some ij, aij, and now here the aij's are greater equal than 0, 1 minus yi, yj over 2. And then we get the negative term. So we get basically plus the expectation over some ij, aij are less than 0, aij. And here we have yi, yj. Which they will cancel out. Over 2. We get the same thing on this side here. And then you basically apply this inequality here, but just flipped. You basically flip this axis and you flip that one. And if you recall how we got there, you see that this is symmetric. So this inequality and that inequality are the same. They work with the same slope if you flip both, right? You get the same graph again. And that's how you prove this inequality. So if you want to see the details, have a look at the Goemans-Williamson paper. It's also in the notes. I might just go and scan them in afterwards and put them up online. I'm not sure whether you want to enjoy my handwriting, though. Okay. So let me actually get to something that's a little bit more fun. And this is 2 research questions, some of which could actually very well be useful for a project that you might want to do. Because I mean, after all, this is a machine learning department, so we might as well, use machine learning in this context. Okay. So the obviously striking thing is that K is a kernel. So we're basically learning a kernel function. Now, what we've done here so far is that we've learned K from an entirely unconstrained set of kernels, right? And the problem is that if some new data comes along, I don't really know what I should do with new data. So now consider the following machine learning version of MaxCUT. You're given a training set. So ML MaxCUT. So my guess is, if you want to do this, this is a low-hanging NIPS paper. Okay, so this is new, unpublished, whatever. We are given a training set of edges aij. We are given vertices v with features phi of xi. So these are some features. They might be more or less complex. And our goal is to find some function y of x such that in expectation over x and x prime drawn from some probability distribution 1 minus y of x prime over 2 a of x and x prime is large. So in other words, the goal is, given those edges which tell us where there's a high cost for a cut, find me a function such that in expectation on unseen data, my cut value will also be large. And preferably get some guarantees for that. So if I didn't have those attributes phi of x, I could just go and, apply the standard Goemans-Williamson algorithm and I'd be done. But this would not generalize because as soon as I see a new vertex, I don't know what I should do. And the only thing I can do afterwards is I can actually apply the optimization problem. Mind you, the same thing also occurs if the data set is really monstrous. Because remember, that's the cost for the SDP, so you might not really want to be able to afford, you might not be able to afford this. So instead, what I'm going to do is the following proxy. I'm going to assume that K is my ansatz. K is given by phi of x, so these are basically all the attributes, transposed some matrix K tilde phi of x. So in other words, it looks like so. Okay. Now if I do this, then obviously it's very easy to extend this matrix to a larger size. The only thing is I will have to prove that whatever holds on my smaller training set will hold in expectation. So now this quantity here can be rewritten as a U statistic. And I can get concentration of measure inequalities for a U statistic. Okay. So I can get the fact that this will be close to its expectations. This is fine. And now I just need to plug this K tilde into the semi-definite program that we had before. There's a price that we are paying. First of all, we might not be able to satisfy the conditions KAI equals 1. This need not even be possible. So we're basically possibly relaxing the problem slightly further. And through that, the problem will get slightly worse. Secondly, this obviously does not find the optimal solution even on the training set. Find the optimal solution on the training set would be the equivalent of overfitting on our training set in general. Okay? But I can actually still go and write this optimization problem. So I get that I want to maximize over, now K tilde has to be positive semi-definite. And here we have sum over I and j, Aij, and now I get 1 minus, phi of xi dot k transpose k tilde phi of xj over 2. And you can see that this can actually be written as an SDP in K tilde. Okay, so this would be a way how you can actually learn the cut for an SDP. Okay. So if you're interested in a project like this, go for it. Yep?
So this is a particular formulation of introducing the features in the kernel, right?
Correct.
You can take any other way.
you could, as long as you have some mechanism of generating a positive semi-definite function, in other words, a kernel, you can do that. So basically, as long as you can engineer some kernel function which will do well on a training set, go for it. This is probably one of the more general ones.
Why do you say it's general?
Well, because, I mean, you probably need to have some attributes. And you want to also ensure positive semi-definite. I mean, proving that an arbitrary function is a kernel function isn't that trivial. So, for instance, if I had a linear combination of kernel functions, right? So if you had something like k of x and x prime is sum over alpha I ki of x and x prime, I can write them already as phi I of x, phi I of x prime, in which case I can actually stack all those up and get my phi of x, and I'm done. And then you'd be solving a special problem relative to the more general feature set that you can use here. You would probably want to use some regularization. But yes, it's not the strictly most general form, but it's one of the more general forms that are still easy to verify that you actually have a kernel. Because in general, proving that some function is positive semi-definite is non-trivial. We're probably not going to do much kernel learning in this class, but you'd probably have to look at the Fourier spectrum, or you'd have to diagonalize it with a suitable eigenvalue, basically relative to the suitable symmetry group. So that's not a fun thing. Okay. So this is one research problem that I think might be quite fun. Another one that's fun is you may or may not have heard of kernel target alignment, or about the Hilbert-Schmidt independence criterion. So in this case, what you usually have is you basically have two matrices. You have a matrix of labels. Let's call this L. Is, phi of label of I, Lij, inner product with phi of label of j. Okay. Now, given this inner product matrix between labels, I might want to find some matrix K that is dependent on L. Or I have some matrix K that is dependent on L. So I have some K, possibly with KII being 1. And furthermore, something for which the trace of K times L is large. Okay. So kernel target alignment does stuff like this. Or the Hilbert-Schmidt independence criterion does this. Yes, you're smiling for good reason. So the thing is, suppose I have some matrix K for which this is large, then the question is, can I therefore... Okay, I suppose I should probably turn off my own phone. Can I therefore design some feature map or some predictor which is well correlated with the data or with the labels? And it turns out that this is the case, because I can now go and factorize K, as in I can turn K into VV transposed. And I then apply again this reasoning up here, which will give me a high probability guarantee that if K and L are well aligned, so in other words their value is large, then I can go and find some labels such that they are well predictive. In other words, if I have dependent random variables, this tells me that a random predictor designed from that function class will be actually at least weakly predictive of what I wanted to predict. Well, which is kind of obvious in hindsight, but it basically means I don't know what it meant. Okay, good. So if you're interested in that, talk to me or talk to Seth rather. Okay, good. Now, last but not least, I'll briefly mention how you can actually use this also to turn it into a solver for 2SAT. You can also turn it into a SAT solver, and that's a little bit more involved. And again, that's in the Goemans-Williamson paper. I just quickly want to show you an example of how you can turn interesting problems into CUT-like problems. Any questions so far? Okay. So that's just enough space and time for 10 minutes. So first of all, max 2SAT. Not 3SAT, but so basically this is effectively you want to find the maximum over y being, binary random variables. So this is in plus minus 1, or basically Boolean to the d. And you have sums over pairs of coefficients, wij, of some Boolean expression involving yi and yj. And then you also have some additional terms that just depend only on, let's say, the yi's. And you want to find the largest value of this. This is not such a completely outrageously outlandish problem. So for instance, if you have a planar Markov random field, a binary Markov random field, and you want to, for instance, do image segmentation, you get exactly that problem. There are more elegant solutions for certain types of those problems. So for instance, Steffi Egelka and Jeff Bilbs have done interesting research on the context of segmentation using submodularity. So there's an ICML paper from last year. So you can look at that. And maybe Steffi will at some point give a teacher class here. But in general, this is the type of problems where you want to actually find y such that this is, well, satisfied. So the Markov random fields, just in case you hadn't seen those things, are of this form. So I basically have some values yi plus 1, and I have some pairwise matching or anti-matching constraint. Okay. Now, what I want to make sure is that I can find an approximately large solution there. For such a planar thing, it's easier if I have then an Ising model. This gets a lot messier, and this, these are special cases of this. Okay. Now, the first thing that I'm going to do is I'm going to rewrite this in terms of products between those variables. Excuse me, could you guys please stay outside? Okay. So the first trick is I'm going to introduce some dummy variable y0, and this is going to resolve whether 1 or minus 1 is true. Okay. So then I can turn this into yi true into a 1 plus y0 yi over 2. For false, I do the same thing with a minus sign. I can do things like yi or yj. And for this, I get 1 plus y0 yi over 2, 1 plus y0 yj over 2. sorry, this is an and, because both need to be true. So if I work this out, this gives me 1/4 1 plus y naught yi plus y naught yj plus y naught squared yi yj. And what you can immediately see is that this term here disappears because it's either 1 or -1. And so if you think a little bit about it, you can get for or, x or, not, and so on, the corresponding expressions. The point is that this is going to give you something of the following form, namely a problem that looks just like our MaxCUT problem. We want to maximize over y something of the form I and j 1 minus yi yj over 2 aij plus sum over I and j 1 plus yi yj over 2 bij. Okay? And then you just happily turn this again into, you basically solve it again with the SDP solver, and you use the same inequalities that we had before, where you apply them once in this direction and once in that direction. That direction is what you need for this here. Okay? And then, by doing so, you get an alpha approximation of a two-SAT problem. For the general SAT solver, it's rather more involved, and I strongly urge you to look at the Goemans-Williamson paper to see the details. It's actually very elegant. Okay, I have a spare copy of that paper here. Okay, whoever wants to have it, take it, otherwise just pass it through. Yeah, maybe not the first one to hang on to it. Okay, so I'm going to see you again on Wednesday. Then we're going to use the fact that if I don't want to store x, but just store the signs of x.w, this is going to give me a hash of x. And this is actually then another prize-winning paper. So it's very amazing that, first of all, this paper, this idea here, it got a fairly substantial prize because it improved the approximation ratio for MaxCUT and SAT and so on by a drastic amount. So it improved it by a factor of 1.5 or so. And secondly, that then the application to turn it into a binary hash got the Kanellakis Prize in 2012. So it's, yeah, it's quite remarkable that one simple idea, namely this thing here, led to so many best paper prizes. Okay, good. So thank you for your attention, and I'll stay around, probably outside, because somebody will